today we're going to be looking at carboxylic acid. So we're going to look at the functional group that is a part of all carboxylic acids. We're then going to look at how to name them, and then some of the properties that they have, and then also the reactions that they take part in. Okay, so first things first, let's look at the functional group that all carboxylic acids have. That functional group looks like this, like so. Okay, this functional group here, we've got a carbon double bonded to an oxygen, and that same carbon is bonded to an OH. This is called a carboxyl group. Okay, emphasis on that ending part, so it's carboxyl. It sounds very similar to carbonyl, so make sure when you're spelling that you are spelling those correctly. If we just break down this carboxyl group, as you can see, that C double bonded to an oxygen, that part is what we call the carbonyl group. So we've looked at that before. So that's the carbonyl part. And over here, the OH is called the hydroxyl part. Okay. So as you can see, a carboxyl is made up, it's a combination of a carbonyl and a hydroxyl group, but these both have to be attached to the same carbon for it to be a carboxyl group. Okay. Just be warned that when we do reactions of carbonyls or the testing for carbonyls, even though a carboxyl group contains a carbonyl, it won't show a positive test for the 2,4-DMP test that we do to test for a carbonyl. Okay, right, so let's have a look at how we name carboxylic acids. So the simplest one is this one over here. So we've got our carboxyl group, it's only got one carbon in the chain. This one here is called methanoic acid. Okay, so number of carbons, and they all end in oic acid, like so. Okay, if we just go to the next one, this should hopefully just be recapped for you guys. If we move on to the next one, where we've got two carbons, so two carbons, this one is called ethanoic acid. Okay, and obviously if we keep going, keep extending the carbon chain, the next one will be propanoic acid, then butanoic acid, and so on. Okay, let's just have a look at how we named some branched carboxylic acids. Okay, so with these, again, we always identify the longest carbon chain. In this one, you always start from the carboxylic acid, so 1, 2, 3. Equally, I could have gone 1, 2, 3. Doesn't actually matter which way. Given the longest carbon chain is 3, it's going to end in propanoic acid. Like that. Okay. Again, when numbering it, make sure you start from carbon number 1. From the carbon number 1 is the one where the carboxyl is, 2, 3. So based on that, the methyl group, the branch, is coming off of carbon number 2. So this is called 2-methyl propanoic acid. Okay. Let's do just one more. I'll make a slightly longer one. Like that. Okay, so again, longest carbon chain, let's identify that. 1, 2, 3, 4, 5, 6. Be careful, it's not the one going upwards. That would be 1, 2, 3, 4, 5. That's not the longest carbon chain, so it's this one going along here. If we number across those, again, carbon number 1 is where the carboxyl is. 1, 2, 3, 4, 5, 6. So longest carbon chain is 6, so therefore this is going to end in hexanoic acid. On carbon number 3, we have an ethyl branch. Okay, ethyl's got 2 carbons. So it's ethyl, so this is called 3-ethyl hexanoic acid. Okay. Just to throw one more in there that hopefully you guys all remember is an exception to the aromatic compounds in terms of naming it. This one over here. In one of the other videos that we covered, where we covered naming aromatic compounds, you should know that this one is an exception. This one here is called benzoic acid. Okay, it's still a carboxylic acid because it has the carboxyl functional group, also has an aromatic ring in it. Okay, right, let's move on. So that's just kind of how to name them. Let's move on to one of the properties that they have. So the properties that we're going to focus on is the solubility of carboxylic acids. Okay, so solubility is can they dissolve in water or not? Okay, and usually what we look at is whether it can form hydrogen bonds with the water molecules or not. Okay, so if we look at a carboxylic acid over here, so I'm just going to go for methanoic acid. Whether they can form hydrogen bonds or not has to do with whether they have polar bonds or not, and whether they have hydrogen and oxygen. Okay, as you can see, this is going to have polar bonds, like our alcohols do, and our carbonyls do, and also it does have oxygen and hydrogen, so it can form hydrogen bonds with water. Okay, so let's just draw our dipoles in. So remember, we've got lone pairs. I'm going to draw lone pairs in as well. We've got lone pairs on our oxygens like that. So this bond over here is polar. This bond over here is also polar, like so. Okay, so whenever you're drawing carboxylic acids out and showing its solubility, make sure you draw all the dipoles in. Okay. If we're showing its solubility in water, you draw one carboxylic acid molecule and you draw another, so you draw one water molecule as well. Again, lone pairs and dipoles should all be drawn in. Like so. Okay, and a hydrogen bond can be between any oxygen lone pair and any hydrogen delta plus. Okay, so I'm just going to go for this one over here. Just draw my lone pairs in slightly bigger, sorry, so you can see them. Okay, so hydrogen bond going from oxygen lone pair to hydrogen delta positive. Make sure that hydrogen bond starts from an oxygen lone pair. Okay, and as usual, make sure you always label your hydrogen bond. Okay, and that is how you're going to show the solubility of a carboxylic acid. Okay, as with alcohols, as you increase the carbon chain, so this is methanoic acid only with one carbon. If I go down to ethanoic and propanoic acid, they're still going to be soluble, but the solubility begins to decrease. Okay, so methanoic acid is the most soluble one. As you increase the carbon chain, it becomes less soluble. They are soluble up to butanoic acid. So when you get up to 4 number of carbons, the solubility begins to decrease. Above that, so pentanoic acid will not be soluble in water. Okay, that's because as you increase the carbon chain is the non-polar component, and therefore it makes the whole molecule, it starts to make the whole molecule less and less soluble. Okay. Let's also have a look at if we have a dicarboxylic acid. Okay, a dicarboxylic acid, if I just draw one out. Also just to name this as well. Okay, so you've got 2 carbons in this chain, so it's going to start with ethan. Okay, you've got 2 carboxylic acids, so it's ethan dioic, so you've got dioic acid. Okay, now if we're talking about the solubility of a dioic acid, so where you've got 2 carboxylic acids in one chain, because you have a lot more dipoles, you've got more hydroxyl groups, you've got more of the C-double-O bonds, that can form more hydrogen bonds with water, and therefore anything that's a dioic acid, they are very, very soluble in water. Okay, so if you've got two carboxyl groups as opposed to one, the one with two carboxyl groups will be more soluble compared to the one with just one carboxyl group. Okay, right, let's just have a look at the reactions that carboxylic acids take part in. Now, given that they are called carboxylic acids, that means they are acidic. Okay, you should know that carboxylic acids are classed as organic acids, because obviously they have the organic chain in them. They are classed as very weak acids. Okay, so let's just have a look at how we can show that these carboxylic acids are weak acids. So that's our methanoic acid. As the structural formula, we always show it as this Cu group. Okay, so the carboxyl group is shown as a Cu. This one here is methanoic acid. As a weak acid, all weak acids will partially dissociate, and that's why we show the reversible arrow. They will partially dissociate in solution, releasing a H+ ion. Like so. Okay, so it's the one at the end of that. So if I just draw this out, it's this hydrogen here at the end of that hydroxyl group. That is the acidic hydrogen, or the acidic proton, we can call it. Okay, so as that dissociates, so I'm just drawing the whole thing out again. That's what it looks like. Okay, and it forms the carboxylate salt. And the carboxylate salt is named after the acid that it was formed from. So this was methanoic acid. So this is called a methanoate. So methanoate ion. Okay. So that's how we can show that carboxylic acids act as a weak acid by showing their partial dissociation in solution, like so. And therefore, our carboxylic acids partake in acid reactions. So any reactions that we've looked at of acids, carboxylic acids will also take part in those. So if we now look at the reaction of our carboxylic acids with metals, so we've done the reaction with metals plus acid, the same thing will apply here. So metal plus carboxylic acid. So metal plus acid will always form salt plus hydrogen. I'm not going to put that in. Just about. Okay, so it's going to form salt and hydrogen gas. Okay, so that's the general word equation for this. Let's now have a look at an example. So if I add calcium metal to a carboxylic acid, so I'm just going to go for ethanoic acid, like that. That's going to form a salt in this case, so it's going to be that H there that goes away. So the salt is got to be drawn out like, so remember calcium has a 2+ charge, so therefore we need 2 of the ethanoate ions for 1 calcium 2+. Okay. And we're also going to form hydrogen gas like that. And now you also have to balance it. So as you can see, we've used 2 of the ethanoate. We're forming 2 hydrogens as well. So therefore, you've got to have a 2 in front of there. Okay. Just a little word of advice. When you're doing these formula of the salts, you can include the charges or you don't have to. So if I'd written this as that would have been fine as well. Okay, but as long as either you got the charges in, both charges in, or you don't have both charges in, that's fine. You can't have one and not the other. Okay. And also to name this, so it was the ethanoate, so it's from ethanoic acid, so this is the ethanoate ion. So this salt here is called calcium ethanoate. I'll just write that at the top here. Okay. Remember, hydrogen, the way we test for hydrogen gas being produced is that squeaky pot test. Okay. So, carboxylic acids react with metals to form salt plus hydrogen gas. That's also a redox reaction, if you remember. Let's have a look at carboxylic acids reacting with metal oxides. Okay, metal oxides plus carboxylic acids will always form salt plus water. Okay, these are the reactions that you have done back at GCSEs of reactions of acids. All I'm doing now is just introducing carboxylic acids to that. Okay, so let's look at an example of this. For some reason, I'm sticking with calcium, so let's go for calcium oxide plus ethanoic acid. So again, you're going to form calcium ethanoate, so CH3. I'm not putting the charges in this time. And you're going to form water as well. Double check that it's balanced. At the moment, it is not, so you need 2 of those there. Okay. So again, you've got calcium ethanoate there. Right, moving on. So given that it's an acid, it will also react with an alkali. So alkali plus carboxylic acids. So by alkali, I just mean metal hydroxides now. So again, these are neutralization reactions. You're going to form salt plus water. The alkali that I'm going to go for is just sodium hydroxide. So sodium hydroxide and ethanoic acid. The salt you're going to make now is sodium ethanoate. I'm putting my charges in. Given that sodium only has a +1 charge, you only need 1 ethanoate ion with that. And H2O like that. Okay, and that is, yep, that's balanced at the moment. Okay. And another neutralization reaction is the one where we have carboxylic acids with metal carbonates. So metal carbonate plus carboxylic acid. So again, base plus acid reaction. This one you're going to form salt plus water. I'm not going to fit this in, sorry. And carbon dioxide as well, because you've got your carbonate here. Okay. So I'm just going to go for sodium carbonate. So that's Na2CO3. I'm going to go for methanoic acid here now. So the salt that's going to form is sodium methanoate, like that. I'm not putting the charges in this time. So you've got your methanoate ion there, you've got your sodium ion there to form that salt there, plus water, plus carbon dioxide. Okay, and again, just double check that it's balanced. At the moment, we've got 1, 2. You've got 2 hydrogens there. You've got 1, 2, 3 hydrogens there. So you need to have 2 lots of this, and therefore 2 lots of that as well. Okay. This reaction, in terms of the observations, given that it's producing carbon dioxide gas, you should observe effervescence or bubbling. You can use either of these words. Okay. This one over here is the test that we use for carboxylic acid. So obviously with carbonyl groups, we would use 2,4-DMP. With a carboxyl group, all we do is we add a metal carbonate to it. So the one that we usually have around in the lab is sodium carbonate. So that's the one that we use. All you do is you just add the sodium carbonate powder to it, and you should observe bubbling. If that happens, that shows that you have a carboxylic acid present. Okay, so the test just going to write that over here. Lost my red pen. Just use this one. So the test for carboxylic acids is this one here. So it's the one where you add metal carbonate to the carboxylic acid and you should observe bubbling or effervescence.